Hi, welcome back to part 3 of our lecture. Now, again, I definitely understand that I talk kind of fast, and I try my best to remind myself not to, but I know that as we're going along, there's places where you would like to pause or hear what I just said again, or see if you heard it correctly. I'll remind you, the magic key J on your keyboard will rewind a YouTube video by 10 seconds. So if you need to wind back 30 seconds or something like that, it's way easier to hit JJJ back up 30 seconds than to be trying to move that little slider in the YouTube controls. That's just not an efficient way to try to do that. Alright, let's talk about our other observing strategy. So far we've talked so much about the in situ techniques for measuring temperature, but let's talk about remote sensing of temperature. Now remember, remote sensing is when the instrument that is doing the measuring isn't actually touching what it's measuring. And again, from climate purposes, this is principally done in terms of satellites. Depending on what classes you've taken at Creighton as part of your environmental sciences curriculum, you may have learned about great remote sensing work that's done using instruments that are mounted on aircraft, for example, or types of radar, for example. Radar is a lovely example of remote sensing instruments where they are measuring the rainfall and so on, and the size of droplets in the cloud and so on, far from the radar station itself. That's all lovely examples of remote sensing, but in practice for climate purposes, it's almost entirely all done by satellite. And the way it is done has to do with Earth's energy budget. You learned back in classes like ATSEVS533 that everything emits radiation, and the amount of radiation that the object is emitting depends on its temperature. Well, the Earth emits a particular type of radiation. It is long-wave radiation in particular. Now, the role of long-wave radiation in the atmosphere is complicated, but a certain amount of that long-wave radiation passes through the Earth's atmosphere and heads out to space where a satellite might measure it. So depending on what how much long-wave radiation the satellite measures, we can work our way backward and figure out what the temperature of the Earth or the atmosphere or whatever that did the emitting of that radiation was. So we're going to study the Earth's radiation budget in great detail in this class, but for now we're just talking about that part of the radiation that is emitted by the surface of the Earth and then emitted upward and gets through the atmosphere and goes out to space. Just as a word to be watching for in the future, we're talking about the atmospheric window here. This is radiation, long-wave radiation that is emitted by the surface and passes through the atmosphere to space. Well, satellites just measure that stuff, and from that we can infer the temperature of the Earth underneath it. In fact, well, this is done all the time. Now, in this particular diagram that I'm showing you here, we're doing it specifically over the water, so it's more complicated to do this over land, although that can be done too. But for example, here we have a nice map showing what the ocean temperature was as monitored by satellites. And we can see all these details that the satellite can infer about, where is it warm and where is it cool and where is there little eddies in the ocean swirling at temperatures around. We can see it at great detail using these satellite remote sensing observations of the ocean's temperature. You can even see little details. I like this little cold current off the west coast of Mexico, and you can see the Gulf Stream off the east coast of the United States. You can see all this detail that might have been missed in the relatively coarse network of buoys. Remote sensing is awesome. A set of instruments, admittedly very expensive instruments in space, can measure properties all around the world. Man, that's a great solution. But you have to be prepared for the kinds of errors that can happen with remote sensing too. I mean, remote sensing of temperature can result in data inhomogeneities too. For example, satellites drift in their orbit. By and large, once they're up there in their orbit, they have little to no control of their position. Well, if the satellite is drifting in its orbit, it may be over a given location at a different time of day than it used to be. So as it goes in its orbit, a lot of orbits, for example, are sun synchronous. They pass over the same location on the Earth every day at exactly 10:30 in the morning. So as they go around the globe, the satellite sees the same place on the ground. But if there's orbital drift, and now instead of it being 10:30 in the morning, it's 11 o'clock in the morning when the satellite passes over, well, you expect the temperatures to be warmer. Right? I mean, there's been 30 more minutes of daytime heating. The temperature should be warmer than they used to be, but that's not evidence of global warming. That's evidence your satellite has a problem. And, well, we can fix that. Once we know that that's going on, there are ways to correct for that. Similarly, satellite instruments often get out of calibration. It's not simple to send an astronaut up there to get a satellite and repair it. By and large, that isn't what we do. We only do that for things like the Hubble Space Telescope, which costs, tens of billions of dollars. A meteorological satellite, what we do is we correct for the problem. We find ways to correct the problems of the satellite getting out of calibration. We can point its instruments, for example, at known sources of radiation, like a fixed star. We know what the flux of radiation from that star is. We now can correct, okay, this is what our satellite says, but that's not right. We know what the right answer is for that star. Now we know how much to correct it, and then they point the satellite back down at the Earth, and we've corrected that calibration problem. As long as you know that there are problems like this, they can be corrected, and it's not actually such a big deal. Okay. Before we move on to part 4 of this lecture, I want to ask a couple quick questions about what you just learned. Remote sensing techniques infer the temperature of the surface based on the amount of blank radiation emitted. Is it long wave or short wave? Make a choice from those two options and get a little feedback before you move on to question 8.